Hi, welcome back to this video series on quadratic residues. Today I'm going to talk about a fundamental property that we will need for constructing other crypto systems like Robin crypto systems. In the previous segment, we talked about how we can use quadratic residues to build a simple crypto system as described by Goldwasser-Mickley. Today I will lay the foundation for more properties that we will need for Robin crypto system. Okay, so the fundamental property is that quadratic residue. What is quadratic residue first? It means that suppose you have a number a, and we call a as a quadratic residue. If we are able to find another number x, such that if you can square x, you get a in say mod p. Okay, p being a prime number. You can assume odd prime number in my discussions usually. Okay, so in this case it's p is a prime. Okay, so a is called a quadratic residue, right? Because we were able to find another x such that x square gives us a. Okay, what kind of properties that I'm looking for in this video segment? Suppose I'm given an a and I'm asked to find such an x. Okay, how do I go about it? It turned out that this problem can be solved when you're working with mod p. So I will take two segments. In the first segment, I will only focus on a much more easier case when p has certain properties. Okay, so let's recall the Euler's criterion. Okay, we have been talking about Euler's criterion in the past, so I will quickly recall that. If p is a prime, right? In this case, this is true. P is prime. We say that if a is a quadratic residue, then we learned that a power p minus 1 by 2 is congruent to 1 mod p. This is the fundamental property of Euler's criterion that we learned earlier. This is true if a is quadratic residue. Okay, not the other way around necessarily. We talked about it in the primality testing. The converse is not true. Okay, if a is quadratic residue, this property must be true. Okay, and p is a prime, then a power p minus 1 by 2 is congruent to 1 mod p. So how can we make use of this property to find this to find the square root of a? Okay, you know what we can do? Let's multiply this equation congruence by a on both sides. That's allowed in modular arithmetic. So what will happen to the left side is that we'll have a power p minus 1 by 2 into a, right, which is a power p plus 1 by 2. You're using the properties of exponent. So this is equal to congruent or equal to a mod p. So I'm just multiplying both sides by a, right? All right. So now we are almost there, but we need to do a little more trick on the left-hand side to solve this equation. Okay. Remember, our goal is to have a in this format, right? A being written as x square. We are not still there. We don't have a square here. Okay. So what if I rewrite this as a power p plus 1 by 4 power 2? This should solve the problem, right? There is a small caveat. Let me explain that first. Okay. So this is basically it. There's one small problem. Okay, what if p plus 1 is not divisible by 4? Then this becomes a decimal, which is not allowed in our system. Okay, and so what will happen in that case is that we need to think about some condition for p. Okay, what if p plus 1, right, is divisible by 4? Well, this means that 0, p congruent to minus 1 mod 4. What is minus 1 in mod 4? Minus 1 means 3 in mod 4, right? So which means that p is congruent to 3 mod 4. Okay, if p is congruent to 3 mod 4, then we know how to solve this equation very quickly using this little trick that I mentioned. Okay, the trick is as simple as this, right? You just take your a because A is the input, A and P are inputs to any program. The program is supposed to find X. Okay, so all you do is you take A and you raise it to P plus 1 by 4, and that becomes your square root of A, because if you multiply these 2 times, you would get A. You can work backwards, right? Okay, all right. So that's first property. Okay, so we know how to solve this equation to find an X given an A mod P, right? Given an A and P, we will be able to find X. It's easier if we assume this property. If we don't have this property, that P is not equal to 3 mod 4. For example, what if P is 13? 13 is not 3 mod 4. This solution won't work, which is okay. There is a randomized solution for that. We don't need it right now, so I will not talk about that. Okay, what is the next property I would like to talk to you? So what you're seeing is my quadratic residue table that I have been using for quite some time. Let me show you quadratic residue of 7, for example. Okay, let's look at the table Z star 7 first. Okay. So what are the quadratic residues of group Z star 7? As always, we will just select the second column, which contains numbers 1, 4, and 2. So the quadratic residues are basically 1, because 1 is nothing but 1 square, 2 and 4. 4 is clear because 4 is 2 square, right? But 2 is also quadratic residue, because 2 can be written as you can see, 3 power 2 is 2, and 4 power 2 is also 2 in 7, right? 4 square is 16, 16 mod 7 is 2, 3 square is 9, 9 mod 7 is 2. So we are clear about this part. Okay, so now we can also apply that little formula that I talked about, right? Let's say our goal is to find the square root of 2 in mod 7, right? This is easy to do because our A is 2 now, right? And what is our PP is 7. Okay, so the formula that we derived allowed us to just plug in A and P to get the square root X. Okay, so X must be A plus A power P plus 1 by 4, right? Let's try that. The whole thing divided by 4. So which means our X must be 2 power 7 plus 1 is 8. 8 by 4 is 2, which is 4. So we have checked X is 4, and clearly 4 square. What is 4 square? 4 square is 2 in mod 7. Therefore, 4 is the square root of 2, which is quite funny when you forget about this mod 7 business. 4 is not a square root of 2, right? But it's happening in mod arithmetic. Okay, so we did find X is equal to 4 becomes the square root of 2 in mod 7. So this formula is working for scenarios where P is congruent to 3 mod 4, which is true when P is 7, right? 7 mod 4 is 3. Okay, we can actually generalize this easily. Let me show you another example. For example, let me plug in say 11. Okay, 11 we know for sure is also 3 mod 4. Okay, so what are the quadratic residues? All we have to do is just look at the second column, right? 1, 4, 3, 5, 9 are the quadratic residues. So let me write it here. 1, 3, 4, 5, or 9. Okay, so these are the quadratic residues, okay, of Z star 11 group. Okay, but we can also now confirm that let's take for example 5. 5 is a quadratic residue because 5 can be represented as power of 4 square, right? 4 square is 16. 16 mod 11 is 5. And 7 square is 49. 49 in mod 11 is also 5. So we did find that 5 is a quadratic residue, and we confirmed it. But we can now apply the formula that we talked about earlier. A power, right, P plus 1 by 4 will give you the square root of A in mod P. So let me now just use the regular Python to do this arithmetic. Let's say A is equal to 5. We are interested in finding out the square root of 5 in mod 11, and p is equal to 11. So all I'm going to do is I'm just going to make use of the power function, right? Power function takes your a, p plus 1 by 4 and p. So hopefully it will tell me the square root of 5 is either 7 or 4. Let's see what happens now. So 4 is coming, which is okay because 4 square, remember 4 square is 16. 16 mod 11 is 5, which is perfectly fine. But we also talked about every element has 2 roots. If there is a root, there must be another root as well. So if 4 is a root, minus 4 is also a root because minus 4 square is the same as plus 4 square. What is minus 4 in 11, which is 7? So 7 square is also 5. Okay, that shows that this formula is working. Okay, now the second important property I want to talk to you is about how many of the quadratic residues actually have square roots that are also quadratic residues. Okay, so this is an interesting problem and it has significant implications in cryptography. Okay, which we will talk about in the next segment when we introduce Rabin crypto system. For example, if you take number 5, 5 has 2 square roots, right? We talked about 2 square roots, 4 and 7. And if you pay close attention to the second column, number 7 doesn't occur as part of the second column. Okay, what it means is that 7 cannot be represented as power of 2. Okay, only 4 can be represented as power of 2 in this group C star 11. So it turned out that when you are working with groups with certain structure, like P is congruent to 3 mod 4, when you take a quadratic residue, for example, number 5 has 2 roots, 4 and 7, but only one of them, right, is also a quadratic residue. Not only 5, this is true also for, say, 9. What is 9? 9 can be represented as 8 square or 3 square. And if you look at the second column carefully, right, you would see what are the square roots of 9? I said 8 and 3, right? You would see that only 3 occurs in the second column. 8 doesn't occur as part of the second column, right? Which is again confirming the fact that only one of the square roots is a quadratic residue. Okay, you can keep trying. We can try a 3. What about 3? 3 has 2 square roots, 5 and 6, because 5 square and 6 square lead you to 3 in mod 11. But only number 5 occurs as part of the quadratic residue set, right? The set of quadratic residues I have given here based on the second column, right? You don't see you don't see 6 here in the set, right? Which confirms the fact that only one of the one of the roots is a quadratic residue. Okay. All right. So we learned a couple of things. We know how to find the square root of a number in mod p, assuming p is congruent to 3 mod 4. We also learned that if a is a quadratic residue, we find x and minus x as roots, but one of the x or minus x is a quadratic residue, not both. Okay, that's what we learned. Okay, that's basically it. Thank you very much for your attention.